We present MeshGPT, a novel generative approach for modeling shapes as triangle meshes using decoder-only transformers. We tackle the task of automated generation of triangle meshes, streamlining the process of crafting 3D assets. GPT-like generative models have shown impressive capabilities in generating text across various languages and even in modeling programming languages, images, and audio. However, the adaptation and application of these models in the 3D domain remains underexplored. With MeshGPT, we teach GPTs to speak mesh, enabling generative modeling of meshes directly as sequences with transformers. To achieve this, we first learn a vocabulary for triangle meshes, which we then use for autoregressive generation of a mesh. We learn a vocabulary of geometric embeddings from a vast collection of shapes. This is done with an encoder-decoder network, which features vector quantization at its bottleneck. We then use the trained encoder and learned vocabulary to train a GPT-like transformer. Once fully trained, it enables the direct sampling of meshes as sequences from this vocabulary. The meshes are interpreted as graphs over faces of the mesh. The features per face of the triangle mesh are extracted using a graph convolutional encoder. At the bottleneck, these features undergo quantization via residual vector quantization. This involves initially aggregating the features across vertices, followed by their quantization and subsequent assignment back to the respective faces. These quantized embeddings are then sequenced and decoded with a ResNet network to predict coordinates of the faces, thus reconstructing the mesh. The stacked embeddings extracted using the graph encoder and residual quantization are sequenced, flattened, and bookended with a start and end token. This sequence is used to train a GPT-like transformer network. Given a start token, the trained transformer is now capable of autoregressively generating geometric tokens as sequences, which can be decoded into meshes. We compare our method to existing mesh generation approaches and neural field-based approaches on the task of unconditional mesh generation. Our approach produces compact meshes with sharp geometric details. In contrast, baselines often either miss these details, produce over-triangulated meshes, or output too simplistic shapes. We show the nearest neighbors to our generated shapes in terms of chamfer distance, verifying our model's capability of producing novel shapes different from the train set. Given incomplete shapes, our model can suggest multiple possible shape completions. We hope MeshGPT will not only elevate the current landscape of 3D content creation, but that it will also encourage more research into direct mesh generation. Thank you for watching.